All right, welcome to this explainer. Look, if you're a focused learner trying to seriously upgrade your network troubleshooting game, you've landed in the exact right spot. Today, we're zeroing in on one highly specific goal. We are going to take your theoretical IP knowledge and transform it into sharp, field-ready diagnostic intuition. We're not just rehashing what IP addresses are, you already know that. We're looking at how they break, why they break, and how you can spot the root cause in a matter of seconds. Honestly, I'm super pumped to dive into this with you, because as any veteran tech will tell you, there's absolutely nothing quite like the feeling of walking up to a totally broken network and knowing exactly how to fix it before you even unzip your tool bag. So let's set the stage with the classic field tech's dilemma. We've all been there, right? You're sweating in some cramped wiring closet. The client is literally tapping their foot right behind you. You check the physical cables, you point at the switch, and, well, you see those beautiful, healthy green link lights just blinking away. Physically, everything is absolutely perfect, but the user is swearing up and down that the computer is totally isolated. It can't print, it can't hit the local server, and it definitely can't get online. How in the world is it possible to have a flawless physical connection, but absolutely zero digital communication? That massive disconnect between hardware reality and software reality? Yeah, that's exactly what we're solving today. Okay, so let's dive right into this. Here's our roadmap for the explainer. We'll start with understanding traffic boundaries, move into gateway versus network isolation, tackle the IP conflict phenomenon, decode the API-PA trap, and finally, wrap it all up with a rapid diagnosis flowchart. So, step 1, understanding traffic boundaries. Let's look at the baseline of same versus different networks. Before we can figure out exactly how a network breaks, we've got to establish the baseline rules of how healthy traffic actually flows. The absolutely crucial starting point in any diagnosis is knowing whether two devices are on the same network or a different one. Why? Because it literally changes everything about how they communicate. Okay, think about the same network scenario. In a local area network, the network parts of the IP addresses match perfectly. Like, say, 192.168.1.10 and 192.168.1.20. Because those network parts are completely identical, these devices can just talk directly to each other through a simple switch or an access point. This is all happening at layer 2. A router? Completely unnecessary here. But shift gears to a different network setup. If one device is 192.168.1.10 and the other is randomly 192.168.2.55, well, that match is broken. Those two devices are completely deaf to each other. You could plug them into the exact same physical switch with brand new cables, and no way, they still can't communicate directly. To bridge that gap, a layer 3 router becomes absolutely essential to route traffic between those two distinct digital islands. Moving on to step 2, gateway versus network isolation, where we'll diagnose the first two deadly errors. Now that we've got the communication basics down, let's jump straight into symptoms triage. We're going to look at these first two errors based purely on what you're actually seeing on the user's screen in the field. First up, a misconfigured gateway. Picture a user who can perfectly print to the network printer down the hall, they can pull files off the local drive, but the second they try to load Google, the connection is dead. What's that telling you? Well, it tells you their device has a perfectly valid local IP, but the wrong gateway. Local layer 2 traffic is fine, but the gateway, which is basically the singular exit door to the internet, is either missing or just typed in wrong. They're entirely trapped inside the building. Contrast that with our second error, a wrong network part. This happens when a device is manually shoved onto the wrong network segment altogether. Maybe someone gave it a .2 address instead of a .1 by mistake. The symptom here, total isolation. You still have those healthy green link lights, but the device is stranded on a digital desert island. No internet, and it can't even talk to the printer sitting 3 feet away. All right, let's turn up the heat. Step 3, the IP conflict phenomenon, also known as the ghost traffic problem. So, what happens when a network isn't isolated, but instead it's actively panicking? Imagine sitting at a workstation. You aren't totally disconnected. Actually, you're supposedly online, but the connection is wildly unstable, completely unpredictable. You load a web page instantly 1 second, and literally the very next second, the whole browser times out. You have to ask yourself, why in the world are packets randomly dropping on an active, supposedly healthy connection? Honestly, it's one of the most frustrating things to troubleshoot because it's just so inconsistent. Well, here's the aha moment. The answer is duplicate IPs. This is a critical error where two devices on the exact same network accidentally get assigned identical IP addresses. It's like two cars trying to park in the exact same spot at the exact same time. They crash. When data packets flood into the network looking for that specific IP, the network switches just get completely confused. The traffic bounces wildly back and forth between the two competing devices. And that chaotic bouncing, that is exactly what causes those maddening, random drops in the connection. Luckily, modern operating systems are pretty clever. They'll recognize this panic state and actively pop up a warning alert telling you another device is using your IP. The second you see that warning, you know exactly what ghost you're hunting for. Next up, Section 4, decoding the API pod trap, or the 169.254 fallback. Let's dig into our fourth deadly error. This one is practically a magic trick for field techs. It's the ultimate diagnostic shortcut. Check out this very specific number, 169.254.x.x. Look, burn this number into your memory right now. Seriously, write it on your hand if you have to. If you open up a command prompt on a busted machine, run an IP check, and spot an address anywhere in this specific range, your troubleshooting time just got sliced in half. Seeing this number instantly confirms a very specific systemic failure on the broader network that goes way beyond the single PC sitting in front of you. So what's the actual background logic here? How does this trap get triggered? Well, step 1. A dynamic device, say a laptop or your phone, connects to the network and immediately shouts out a broadcast request, practically begging for a valid IP address so it can join the party. Step 2. The router, or the DHCP server, flat out ignores it. It fails to respond. Maybe the server crashed, maybe the uplink cable is literally severed, or maybe the IP pool is just completely maxed out. Step 3. After a few tries with 0 answers, the computer basically just gives up waiting. But instead of crashing or sitting there with a blank IP, the operating system auto-assigns itself this temporary fallback address starting with 169.254. It intentionally isolates itself so it doesn't cause any network conflicts. So, the absolute second you see 169.254, you stop troubleshooting that local computer's network card. The hardware is fine. The server is ignoring the client. You just get up, walk straight to the server room, and fix the DHCP's service. Finally, Section 5, Rapid Diagnosis Flowchart. Let's look at your field tech decision tree. Let's pull all of this together into a real actionable takeaway. This is a simple but incredibly powerful decision tree, and I promise you, memorizing this will save you hours of wasted effort. When you walk up to a machine with no internet, step 1 is always, without fail, check the IP address. Pull up the command line, see what you're working with. Step 2, look closely at that address. Is it 169.254.x.x? If yes, boom, you immediately know you have a DHCP or router communication failure. Stop messing with the PC, go check the central server. But if the answer is no, meaning you've got a perfectly normal-looking IP, you just smoothly move to step 3. You check the gateway and the network part alignment against the subnet mask. And talk to the user. Ask questions. Can they print locally but have no internet? Right, that's the gateway hiding the exit door. Are they totally isolated with a normal-looking IP? Their network part is misconfigured and they're stuck on that desert island. This mental flowchart empowers you to systematically, absolutely crush these 4 errors without wasting a single minute just guessing. Which brings us to our final takeaway for this explainer. Green link lights only mean physical connectivity is good. If the network part is misconfigured, the device remains completely isolated digitally. You can't let the hardware fool you into a false sense of security. Physical wires mean absolutely nothing without the precisely correct digital matrix flowing over them. Master that difference between Layer 2 and Layer 3, memorize that 169.254 APPIA address, and always keep an eye out for duplicate IP ghost traffic. So the next time you see those healthy green link lights blinking away in a server room, you've got to ask yourself, is the digital matrix actually flowing, or am I just looking at a really beautiful mirage? Keep questioning the hardware and stay curious.